Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. So the theme for this lecture is that privacy loss is a random variable. So this is our definition of the privacy loss. It's the log of the ratios. So it's a random variable. What does epsilon 0 differential privacy guarantee? It promises that this random variable is bounded by epsilon. Now, sometimes the privacy loss could be negative, at least intuitively. So, for example, formally, this can happen because this log might be negative. Maybe the numerator is smaller than the denominator. So suppose, for example, that the adversary knows that we are in one of the following two cases. Either the number of people in the database satisfying property P is K, which is the gray, which then gives the gray probability distribution when we add Laplace noise, or the number is K plus 1, which gives us the red probability distribution. So suppose the true answer is K plus 1. Then outputs that are more likely under the gray distribution than they are under the red distribution will give us a kind of negative privacy loss. It says that the coin flip is kind of helping even a little bit extra to hide that person's presence. Okay. So I want to exploit the fact that this is a random variable and sometimes it can be negative. It's a bounded random variable and sometimes it can be negative. So let's review the definition of the KL divergence, the Kolb-Black-Leibler divergence. It's not symmetric, so KL, here y and z are two different probability distributions. All right? And the way I've written this part of the slides, I'm assuming that the probability space is discrete. Everything is more or less the same with continuous, but it's just easier to write it this way. So suppose, for example, that y is the distribution on outputs of our epsilon 0 differentially private mechanism when the database is x, and z is the distribution when the database is a neighboring x prime. So the KL divergence is just the expectation of the log of these probabilities. So it's the worst case over all adjacent x prime. In the worst case over all adjacent x prime, the KL divergence will be a bound on the expected loss of the algorithm, right? Because that's what we're summing in here. Something's bothering me. I'm missing a term, right? I need a term there. The probability that y is equal to y. Oh, it's in the expectation. Right. Okay, fine. Great. Okay. So it's by, this is by definition an average notion. And so that means that bounded KL divergence does not necessarily ensure differential privacy. And the literature contains other average notions of privacy loss. So, for example, definitions based on mutual information. And whenever you see somebody give you a definition that's an average case notion, you should check. You should say, what happens to an outlier? Is the outlier protected? A lot of times these average case notions specifically fail when you've got some weirdo in the database. And the problem is that it's the weirdo who particularly needs the protection. So this is just something to keep in mind. All right. We define a worst case notion of the divergence, which we call the maximum divergence. And that's just the maximum over all of the events S in the support of Y of this ratio of probabilities. Okay, so this is a worst case notion. And a randomized algorithm is epsilon 0 differentially private if and only if for every pair of adjacent databases, the max divergence is bounded by epsilon. Okay? It's just an equivalent definition. So what we want to prove now is that the expected privacy loss, so privacy loss is our random variable. We want to prove that the expected privacy loss is going to be something like epsilon squared if the worst case privacy loss is epsilon. So in other words, if you have an epsilon 0 differentially private mechanism, then the expected privacy loss of this mechanism is going to be bounded by 2 epsilon squared. So let's just go through the proof. First of all, by definition, the KL divergence is this quantity. It's the probability under distribution D of C and Q times the log of this ratio, summed over all Q. And from the log sum inequality, we know that this is at least 0. It's non-negative. So that means that the KL divergence of D with D prime is at most the sum of the KL divergence of itself plus some term, which is at least 0. All right. So now we're just pulling off from the definition. We simply are summing both of these terms now over all Q. So it's a straight expansion. In this step, what do we do? We subtracted off a D of Q times the log of D prime of Q over D of Q. Okay? And we also added it back in. So we didn't make any change. All right? But of course, this is just 0. So this term goes away. And we're bounding D prime of Q minus D of Q by the absolute value of D prime of Q minus D of Q. And we're bounding this thing by epsilon, because it's an epsilon differentially private mechanism. Okay? All right. So going back to this absolute value, we're bounding that. You can sort of plug in. This is at most the maximum minus the minimum of those two terms. Right. Okay. So then we use the fact that this max is at most e to the epsilon times the min, because it's an epsilon differentially private mechanism. Then what did we do? Oh yeah, we regrouped our terms. That's all. And then finally, we use the fact that this is a probability distribution. So this thing summed over all Q will be at most 1. And that gives us our bound. Okay? So this is going to be really powerful, because we're going to be able to start doing stuff by saying, well, what do we really expect is going to happen? Oh, really, we expect the expectation loss, not this worst case loss. So this is just a recapitulation of what we said before. Now, this measure is kind of brittle, in the sense that if we make a small change in the probability space, we could make a really, really big difference in this measure. So for example, I could take, for some event S, if Z doesn't have a whole lot of probability for that event, I could like modify Z and make it down to 0. It's a small change in the probability distribution, but now I'll have a 0 in the denominator. Okay. So it's very fragile. And it makes sense to relax it a little bit. And we do this, we call it delta approximate max divergence. And basically what we're saying is this condition that we wanted so much to hold, that the ratio would be bounded by e to the epsilon, well, we want that to hold almost everywhere, except we'll give up on it in some little region of size delta. So formally, that's what we have here. We define this to be the maximum over all s in the support of y, but only require it for these events s where the probability under y is at least delta. If the probability under y is less than delta, then we just have no condition, no requirement. Yes? I'm sorry? How is this a worst case notion? Why do you think it isn't? If they're very divergent, then this simply won't hold. There will be more than some delta region of the space in which this ratio fails. How does it fail? So if there's a region of the space, so think of an event that can happen under the distribution when the database is x, but it cannot happen when the distribution is x prime. If that event has a big probability, a probability bigger than delta under x, then that event s would be one of this type. The probability is bigger than delta under x. But this logarithm, we'd have a 0 in the denominator. We'd have a non-zero thing here, but a 0 in the denominator, so it would fail. So another way of saying this is what I have here at the top of the slide. We define epsilon delta differential privacy. We said the mechanism gives epsilon delta differential privacy if for all pairs of adjacent databases, this condition holds, that the probability of an event under x is bounded by e to the epsilon times the probability under x prime plus this delta term. And when you shift these things around, you see that you get exactly this expression. You subtract the delta over here and then divide through by that probability, and you get this. So this delta approximate max divergence is another way of saying epsilon delta differential privacy. And this epsilon delta notion comes up a lot, and we'll see a couple of reasons why. And the notion of differential privacy that we've been talking about until now simply has delta set to 0. And that's why I kept dragging around that epsilon 0 notation. Okay. So here are some, yes? Right? So I'm not sure I understood you, but it says that with probability 1 minus delta, the ratio will hold.
Because you are adding data, so data is not the probability mass where the epsilon differential privacy.
That delta is the mass where the guarantee could fail. That's right. And if it fails, it can fail spectacularly. The definition permits it to fail really spectacularly in the case that the bound epsilon is not observed. It could be infinite even in that region. So here are some things to think about. first of all, think about like it's kind of an order of quantifiers. So this says fix x and x prime. Once they are fixed, the probabilities, with probability 1 minus delta, the privacy loss will be bounded by epsilon. And again, the probability space is the coin flips of our mechanism. This is a little bit different than with epsilon 0 differential privacy, which says fix x, and now for all x prime simultaneously, the privacy loss will be bounded by epsilon. So it's definitely a weaker promise. I should note here that although the definition doesn't say so, in the literature, we take delta typically to be what we call cryptographically small. That is, it's some function that grows more slowly than 1 over any polynomial in the size of the database. Okay. So you should think of it as something that should be extremely rare. You wouldn't expect it to happen. Just like when you use a public key crypto system, you don't expect the adversary to guess the decryption key. It's just very rare. Yes? Definitely weaker.
So what are we gaining by giving a weaker guarantee?
You'll see. I want to just talk a little bit more about ways in which it's weak and what it isn't doing, and then I'll tell you what it does do, okay? So here are two possible worlds. Cynthia is in the database. The database is X. And here are various properties. Cynthia does not have property P1. She has property P2 and P3, but not P4, and so on. So that's what happens under X. Now consider some alternate reality in which maybe she has properties 1 through 4, but not 5 through 8. Now, suppose we run, so this is reality. This is an alternate reality, but this is the real reality. Suppose we run a set of counting queries, and we add noise. We're not going to add enough noise. The noise won't be the great noise that we've been using for epsilon 0 differential privacy. Somehow it won't be good enough for that, all right? But it'll be symmetric. Now, suppose that the noise has the following property. It's positive when we do the releases for the first 4 queries, and it's negative when we do the releases for the next 4 queries. Okay? So, in other words, the noise agrees with the alternate reality. So if we chose the alternate reality after the fact, we could make the sequence of outcomes that are seen much more likely than they would be under the true database X. And that's why it's so important that we fix X prime in advance to make sense out of this. So what I'm saying is, if I am in the database and you do ask these queries, there is some alternate me that is somehow or other a much more likely explanation of this data than what you saw. A much more likely explanation of the data that you saw than the truth. But it's not very meaningful. But in any case, this is to try to illustrate the difference between epsilon delta and epsilon 0. You just won't have this with epsilon delta, with epsilon 0 differential privacy. Our noise will be such that we'll guarantee that it doesn't happen. So the semantics are a little bit, this very big difference that I just illustrated is a complexity that arises when the data rows are very complicated. Like, there was a whole lot of information about me, and I had some properties and I didn't have other properties, and all kinds of combinations were possible. If my data in the database were simply a single bit, then there would be very little difference here. There's only one alternate world with respect to me. It's just the fact that there are many alternate worlds with respect to me that makes this difference that accentuates this difference. Okay, so to answer your question, why do we care? Why did we do it? Because it's a weaker privacy guarantee. So it turns out that there are a lot of things that you might want to do algorithmically that this is really helpful with. I'll give you 3 examples. So the first one we call, propose, test, and release. Before I explain this, I should say something that you might have been wondering, and I think somebody might even have asked on the first day, and today is the day to talk about it. We have a database. We have a function that we want to compute on this database. On this particular database, there is no neighbor, no immediate neighbor that gives a very different outcome. There exist pairs of neighboring databases for which the sensitivity is high, but this database is not an element in such a pair. So what we really would love to be able to do is to somehow add noise that sort of just covers the distance between this database and its neighbors, and not between the worst case pair of adjacent databases. Now, so let's call that kind of more local notion. In the literature, it's called local sensitivity. I prefer the term instance sensitivity. And here's an exercise. It's not safe to add noise that is simply scaled, Laplacian noise that's scaled to the instance sensitivity. So if you have any idea why, give that some thought. I'm sorry?
If the noise is modeled on the instance of the database, it would be just be a scaled version of the actual information, and the adversary might be able to subtract this entire noise from the entire database as well.
You're going in the right direction. It's not an exact answer, but you're in the right direction. Try to think about a concrete example where I don't want to say it. Just think about it a little bit, but you're definitely in the right direction. So one approach to dealing with this is called smooth sensitivity. This was an approach proposed by Nissim, Raskolnikova, and Smith. And I'm wondering if I actually wrote something about this. Yes. So what they say is somehow you add noise in a very smooth envelope around the instance sensitivity. And I should just explain my picture. I'm sorry, I didn't do that. So here we have 2 neighboring databases whose image under F are very close. Here we have some other neighboring databases whose image under F is very different. And the goal is that we want, when we can, we want to add noise that's more scaled like this. That's what this picture is about. So this, so there's this framework called the smooth sensitivity framework. And it's very elegant, and it's also a little bit hard to work with. So there's another approach, which we call propose, test, and release, which basically is a quick and dirty alternative to the elegant and beautiful work of Nissim, Raskolnikova, and Smith. And the idea is this. You want to come up with a differentially private test to see whether the local sensitivity, the instance sensitivity, this instance, is small. So it has to be a privacy-preserving test of insensitivity. And then if the algorithm says, yes, yes, the local sensitivity, the instance sensitivity is small, you can then take the next step and add small noise. And if it says, oh, I can't promise you that the instance sensitivity is small, then the algorithm says, all right, I'm going to use maybe the technique of Nissim, Raskolnikova, and Smith, or I'll do something else. Or maybe I'll quit. Why would quitting at this point be a good idea? Let's think of an example where it's exactly the right thing to do. You have a database drawn from some population, and you're trying to find the median for the values in your database. Now, if your distribution is very bimodal, you might have a whole bunch of people over here and a whole bunch of people over here, and kind of nothing here at the median. All right? Is the median interesting in this case? Is it a meaningful statistic? No, it's not meaningful. You really here have two populations, and you want the medians of each of them. So in some sense, if you're looking at the median, it might be perfectly reasonable to say, no, I don't like this situation. This is the wrong kind of data set for a median. Obviously, the underlying distribution has no mass at the median. Forget it. On the other hand, it turns out this is the only problem. As long as there's positive density at the median, the median does make sense. So what you can do is, using this PTR example technique, is to say, is the current instance, so let's say that our numbers are between 0 and 1. Everybody's value is between 0 and 1. You could say, is the current instance far from one with, let's say, sensitivity of 1 over n, the cubed root of n? And this question, is the current instance far from, or how far is the current instance from a different instance where the sensitivity is less than 1 over cubed root of n? That's just a sensitivity 1 query. How many people do I have to change in order to get myself from this instance to one that's sensitive? How many people do I have to change? That's a counting query. Okay. So you can use Laplace noise for that, right? Well, sometimes, and then if the answer comes back that says, oh, you're really far, you're like log squared n away from such a thing, then you can say, great, I'm going to use noise that's scaled to 1 over cubed root of n. Now, why is this whole thing not actually epsilon 0 differentially private? Why is this algorithm not epsilon 0 differentially private? Well, when I asked that counting query, how far am I from a database that is sensitive? There's a Laplace that's added to the answer. Maybe my database is really sensitive, but for some, terrible reason, the Laplace happened to give a big value. When I sampled from the Laplace, I got log squared n, or, log squared n over epsilon. So I kind of got a false reading of insensitive. It's very unlikely, but it could happen. This is one case where we would love to relax to epsilon delta differential privacy. Something could go wrong, but it's really unlikely. That's one example. Here's another one. So we're going to prove a really powerful theorem. And in fact, you've actually seen almost the entire proof already this morning. We call it the advanced composition theorem. And it has a qualitative and a quantitative aspect. So qualitatively, so far, when we've been talking about composition, most of the time we've been conceptually thinking about many queries to the same database. But I did mention early on, the first day, that you actually get composition for free over completely non-communicating, separated databases. If I have one database over here with Ravi Kannan's data in it, and it's epsilon 1 differentially private, and another one over here, I said, with Ravi's data in it, that's epsilon 2 differentially private, then the universe as a whole is still at least, at worst, epsilon 1 plus epsilon 2 differentially private. So we want to sort of really capture the sense in which things are working over multiple databases. So we're going to look at a situation where the adversary can repeatedly create databases even and choose which mechanisms are going to run on them, and still cumulatively it won't get a whole lot of information. And when we do that, we can start answering questions of the following form. Consider Bob, who goes through life and over the course of his lifetime takes part in, say, 10,000 epsilon prime 0 differentially private databases. And suppose I want his lifetime cumulative epsilon loss to be 1. What should I choose epsilon prime to be? That's the kind of question we're going to be able to answer when we prove this theorem. Quantitatively, the theorem says the following. First, let's think about it setting delta to 0. When we do that, it says if we have k epsilon 0 differentially private mechanisms, then for every delta prime, their composition, which we will define when I tell you how we're going to, that was the qualitative part, how do we model composition? Their composition will be at worst 2k log of 1 over delta prime times epsilon plus something bounded by k times epsilon squared, delta is 0, plus delta prime, comma, delta prime differentially private. So we're getting something that looks a lot like square root of k times epsilon plus this term, comma, delta prime differential privacy. Not blah, 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 0 differential privacy, only this relaxed notion. Now, when we look at composition of epsilon delta differential mechanisms when delta is not 0, those deltas show up here. Now remember, they're supposed to be cryptographically tiny. And k is something that actually happens in a lifetime. So k times delta is also going to be really, really tiny. And we're actually looking at delta prime, or something like that. So the key point here is that the thing that's multiplying epsilon looks more like square root of k than it does k. Yes, it has this log of 1 over delta prime term, but it has only a square root of k. If we choose, now over here we have k times epsilon squared, something that's at most k times epsilon squared. So if we choose epsilon prime to be epsilon divided by square root of k, then this term and this term start looking like they're in approximately the same ballpark. And we're ending up with something that is more, or whose dependence on k is square root of some constant times k. Okay. So that's what we're aiming at. So here's how we modeled adaptive k-fold composition. We think about it as a game between the adversary and the universe. The universe has various databases. No. The adversary and the universe. The very first thing the universe is going to do, it is going to flip a coin and choose 0 or 1 with equal probability. It does not tell the adversary the outcome of that choice. It knows it. Now the adversary produces a pair of adjacent databases, x10 and x11. The first subscript 1 says that this is the first round. And it has a 0, 1 in the first round and a 1, 1 in the first round. It also presents to the universe a differentially private mechanism, M1. The universe, according to the choice of B that was fixed in advance and that the adversary doesn't know, takes this mechanism, uses B to select among these two, applies the mechanism to the selected one, and gives the response. That's the first round. Depending on what it has seen, the adversary chooses a new pair of adjacent databases, x20 and x21, and a new mechanism, and gives this to the universe. And the universe, using that same B that it fixed in advance, selects from this pair, applies the mechanism, and responds. And we iterate k times. That's k-fold adaptive. Adaptive because the adversary is adapting its choices of databases and mechanisms. Composition. All right? The adversary's goal in life is to guess that secret bit B. That's all. What?
The B is chosen just once and the adversary can keep on querying and the B will not change.
The B does not change.
Ma'am, here guess B. So basically, ma'am, we will guess it with the probability half, like either 0 or 1.
He could do that, and then he would have no advantage. I mean, he would just have a 50-50 chance. The adversary wins if he kind of substantially beats a 50-50 chance. So one way to think about this. So first of all, we gave the adversary a lot of power here. That's just for show. It plays absolutely no role, it turns out. The only thing that's really going to matter is that we have independent, the random variables in each step in this direction are chosen independently of each other. That's the only thing we're actually interested in. But one of the things that this, if you simplify it, it could model that maybe B equals 0 is the real world, and B equals 1 might be the world in which Bob's data in every single database that he participates in is replaced with junk or deleted. Okay? And we're trying to say that the adversary can't tell the difference between the real world and this junk world. All right. So the proof of the composition theorem, as I said, you've essentially seen the whole proof already. Let's look at the epsilon 0 case. So our mechanisms, M1, M2, that the adversary chose on the previous picture, they're all epsilon 0 differentially private. So what do we know? Each one is epsilon 0 differentially private. So for each one, the expected privacy loss is bounded by 2 epsilon squared. That was the lemma that we proved earlier. So we modeled the cumulative privacy loss as a martingale. We have a bound on the maximum loss, that's epsilon. We got that from the fact that it's an epsilon 0 differentially private mechanism. We have a bound on the expectation. We got that from our lemma, 2 epsilon squared. And now we applied the Azuma-Hufting bounds, which says what? That the probability that our cumulative loss, the sum over our privacy losses of all of the MIs, all of those mechanisms, minus k times this bound, you can kind of think about that as, well, I'll be quiet, minus k times this bound, the probability that this quantity in absolute value exceeds any z times the square root of k times the expectation is exponentially small in z squared over 2. And this is essentially what the same kind of theorem that Sanjeev was referring to yesterday. These are turn-off bounds. And the only thing that we really need here, again, is that the privacy loss at each step is independent bounded random variables. Okay? So my fabulous animation, there's my privacy loss. So, you know, it's a random walk. It goes sometimes to the right, sometimes to the left, but it doesn't ultimately drift all that far from its expectation. How about the epsilon delta case instead of epsilon 0? So there ought to be a way using some generalization, of proving it using some generalization of these bounds. The way we did it in the paper was, I'm sorry, I forgot a word. Uses what's something called the dense model theorem for distributions. And basically what it says is, if these things have delta approximate max divergence from each other, then in particular, there is a y prime which has max divergence epsilon and that is statistically close to y prime. And we use this thing k different times, and that's where we end up with our k deltas in our bound. And we would have to go through a lot to prove it, and we don't need to. Okay. So here's something to think about. We've pictured in the upper right our little interactive game that we have in k-fold adaptive composition. And we said that it sort of hides the presence of Bob's data or my data. So I'm in various databases, and this thing hides my presence or absence or hides the value of my data. What it is not doing is hiding simultaneously my absences in all of the databases that I don't participate in, right? So in some sense, it's a little bit like the kind of phenomenon that we had with epsilon and delta. It says fixed two alternate realities, you're not going to be able to distinguish between them. We're going to come back to something of this form either on the last lecture or in a problem session that day. But, I mean, this really is food for thought. Think about what does it mean. I don't really know what it means. I have, you know, some days I think I get it, and some days I know I don't understand it. But of course, I can't be everywhere. That's humanly impossible. So let's just think about it. I don't have conclusions to tell you about this. Okay, a third relaxation, a third use of epsilon delta differential privacy. The addition of Gaussian noise rather than Laplace noise. So we've seen the first theorem before. Delta 1. Here, f could be a function that maps x to some point in high-dimensional space, d-dimensional space. We defined the L1 sensitivity, delta, which we were calling it before, but now I'm going to emphasize that this is the L1 sensitivity, as the maximum over x and x prime of the L1 norm of f of x minus f of x prime. We can also define delta 2 to be the L2 difference between them. Right? Whereas when we're using Laplace noise, delta 1 over epsilon, yes, delta 1 over epsilon in every component in order to get epsilon differential privacy, we're going to add noise using somehow defined by delta 2, but it's going to be normally distributed with 0 mean in order to get epsilon delta differential privacy. And this theorem says that it's sufficient for the variance to be delta 2 over epsilon 2 quantity squared. Remember that the standard deviation is going to be the square root of that. It'll be our normal, what we're used to, delta over epsilon term, only now it's delta 2 rather than delta 1. And then it'll have something that depends logarithmically in 1 over delta. Okay. Now, let's prove this theorem. Because everybody refers to it, and to my knowledge, there's actually no proof in the literature. Oh, before I prove it, I just want to point out, why is it a gain? Why might it be a gain? Well, before we had the composition theorem, it would be a gain. Now that we have the composition theorem, we understand that we can get similar bounds by composition of epsilon 0. But before we had that, we didn't know it. We didn't know that you could still use Laplace noise for that. So it seemed to be giving us a gain because, let's say, if you think about k arbitrary sensitivity 1 queries, like counting queries, the L1 sensitivity is k, and the L2 sensitivity is at most root k. So it seemed to be buying us a lot. It still buys us something in that, well, actually. Okay, privacy loss with Gaussian noise. Good. I want my privacy loss to be bounded by epsilon. My privacy loss is the log of sort of the mass at x. Well, I'm sorry. X here is a scalar. It's not a database. I have 2 databases. We're looking at the one-dimensional case. So we're computing some function that's real valued. And the databases will differ by, the value of the function will differ by at most delta f. In the one-dimensional case, the 1 norm is the same as the 2 norm, so I didn't bother with the subscript. Okay. So, I need to see when is the ratio of these densities bounded by epsilon, where the densities look like e to the minus x squared over 2 sigma squared in the numerator, and in the denominator, the exponent has that extra delta f term, right, which gets squared. So taking logs, we get this, taking logs and expanding out the x plus delta f squared and subtracting off, we end up with this expression, right? 1 over 2 sigma times 2x delta f plus delta f squared is bounded by epsilon. In absolute value is bounded by epsilon. So one way that this will definitely happen, if you sort of do this arithmetic through, is when x in magnitude is bounded by this. This is just a reworking of that. It's going to happen over here for exactly the same reason, but we're going to get a little bit of extra mileage over here because the situation isn't perfectly symmetric. But we do know for sure that if this is the case, then while x in absolute value is bounded by that, the privacy loss will be bounded by epsilon. There will be other cases where it's bounded by epsilon, but it's at least in those cases. So to ensure epsilon delta differential privacy, it's enough to ensure that this condition will hold that this will fail with probability at most delta, all right? That it will have a greater than rather than a less than with probability at most delta. Now plug in absolutely standard tail bounds and just do the arithmetic, and it will end up showing that it's sufficient for sigma squared to be as large as delta f over epsilon squared 2 log of 2 over delta. Okay. Just nothing magic there. Okay, how about the high-dimensional case? Miraculously, you heard the proof of that yesterday, sort of. You heard the key to the proof yesterday. So how are we going to go about the high-dimensional case? In the high-dimensional case, and this is the, we're adding a high-dimensional Gaussian. That is, we are sampling along each of these different, for each of these answers, we're doing another draw from the same Gaussian. What? Did I hear some suggestion? So we could think of the total noise vector that we're adding as a sample from a spherically symmetric Gaussian. Okay, well, let's set it up. I took what I had on the previous page, slide, and I just put norms around everything. Right? So the privacy loss will be bounded by epsilon whenever this holds, or equivalently when that holds. All I did was put norms around everything. And here, the vector v is any vector whose length, whose Euclidean distance length is at most delta f, because we're now working with the L2 sensitivity. So we're going to use the fact that this Gaussian, that the spherically symmetric, that this noise that we've added, which we did by adding independent Gaussians in one dimension, d times, that it's spherically symmetric. So we could pretend that we chose one of these orthonormal components to be parallel to our sort of error vector, our noise vector v. So let's draw this. What I'm going to do, so again, I'm now choosing an orthonormal set of basis vectors. I mean, it's just a thought experiment, but it's equivalent to what actually happened. So we've got this orthonormal set, b1 up to bm, and b1 is parallel to v. So our vector is the sum over I equals 1 to n of lambda I bi, where this guy is parallel to v. And lambda I was distributed as normal of 0 sigma squared. Sigma squared. Okay? So we're looking for a bound we want to upper bound this difference. So here's my picture. Remember, I've got an orthonormal basis. So I can slightly decompose x to its part that's parallel to v and everything else. So this is x. It has a lambda 1 b1 term, and then the other lambda I bi's. b1 was chosen to be parallel to v. So I can just line v up over here. And now this thing is simply x plus v. And now we know how to do this. What is this term? Well, it's the sums of the squares of the lengths of these guys. This is the sum of the lambda i's for I greater than 1, plus lambda 1 plus the length of v quantity squared. That's the square of x plus v, right? And x squared is just the sum of the squares of the lambda i's. Do the arithmetic, you end up with the length of v squared plus 2 times lambda 1 times the length of v. But we chose v. V is anything whose length is bounded by delta f. So this ends up being bounded by this. This is exactly the expression we had in the one-dimensional case.
to derive that, you can just take x plus b line squared is just the dot product of x plus b and stuff.
Yes.
So then you get this.
Yes. Yes. That's true. That's another way. Right. Okay. So now you have two proofs, neither of which is in the literature. Good. All right. Ooh. Okay, so now I want to take a closer look at this. I'm looking here at cheating. So instead of having that log of 1 over delta term floating around, what happens if we drop it? So let's look at trying sigma equal to delta f over epsilon. It turns out in that case, doing the same computations we did, we're going to have our privacy loss bounded by epsilon when this occurs. And for exactly the same reasons as before, this will happen when the absolute value of x is less than sigma times 1 minus epsilon over 2. All right. Just to give you some idea of some numbers and the motivation, why am I even thinking about dropping that log of 1 over delta term? If I don't drop it, what happens if I want to ask a number of counting queries, say 10 of them? And I'm going to take epsilon equal to 1 and delta 0, then I get noise of 10. If I take epsilon equal to 1 and delta, sorry about that minus sign, equal to e to the minus 10, then I'm going to end up with noise about 20, bigger than 20. So it's actually worse. It only starts to become good when k gets very big, very big. So that's the motivation. So let's look at this a little more carefully. What happens when x is outside of that range? Did the world blow up? Did we fall off a cliff? No. Most likely what will happen is that instead of having privacy loss of epsilon, we're going to have a privacy loss of 2 epsilon. The Gaussian degrades really nicely, and very gently. So really, really bad things aren't going to happen. Or at least really bad things will happen only with insanely small probabilities. So if you look in general at the probability that your privacy loss is less than or equal to k epsilon, rather than just plain epsilon, then you end up with something that looks like this. So I have a k instead of a 1. All right? And this probability is about 1 over k e to the minus k squared over 2, roughly, by standard tail bounds. So this looks pretty Gaussian itself. Right? Looks like a normal Gaussian. So in some intuitive sense, the privacy loss, the behavior of this privacy loss random variable is not worse than that of a standard Gaussian. Then, it's kind of like you can describe it, bound it by a standard Gaussian. And this suggests a current area of research, which is kind of a different relaxation. We had epsilon 0 differential privacy initially. We relaxed to epsilon delta differential privacy. But epsilon delta differential privacy allows terrible things to happen in the delta region. So it's very, very, very good, and then nothing is guaranteed. And here we're saying, let's try a different relaxation of epsilon 0. We're never going to, the remoteness of the horrible is going to be extremely small. but we're going to degrade gracefully. And we're calling it concentrated differential privacy. So I'm not going to give you a formal definition because it's not done yet. This is very, very current question. But we did play with it using these Gaussians. And a guy put it into Excel, and he came up with a nice drawing. First of all, this is what happens with the cumulative distribution of the privacy loss. Let's see if I get this right. So in epsilon 0, there's no probability that the privacy loss will be less than -1. There's no probability that the privacy loss will be bigger than 1. And it does something or other in here. We don't know because we don't know what the mechanism is. There's no promise. All we know is that it lies in this range. Right? And, I guess we know something about its expectation. I think here epsilon is 1 in these examples. Okay, with epsilon delta, there is some probability that you could have big privacy loss. Sorry. This is the probability, yeah. And with concentrated differential privacy, you sort of move smoothly in here. So we were thinking about this in the context of the problem of you have a medical database, and this is a real problem. You have a medical database, say a hospital database, and your researcher wants to know, does the hospital database contain enough people with certain criteria, satisfying certain criteria, in order to run a particular medical study. So the researcher actually has in mind a specific study that they want to do, and they need so many, 200 people who have who satisfy some set of conditions. And it turns out that in the United States, even to find out if the database has enough people for you to try to convince some set of them to join your study, big enough set of them to join your study, just to get permission to find out if there's enough to even bother trying, you need to go through what's called an IRB, an Institutional Review Board. So that's a time-consuming, difficult process. So what if there were a privacy-preserving way of simply finding out, is it worth your effort to even try to go and recruit people for this study from this hospital population? So if there were a privacy-preserving way, you could at least find out if it's worth your effort without actually going and getting this IRB approval. So what happens when, in real life, when they try to do this? Forget about the privacy part. Suppose they have IRB approval. What happens in real life? They do some kind of, so they have approval, they do some kind of counting query, and they're trying to figure out, are there enough for their study? They need 200. Well, they can't tell for sure. Even if there were 225 people in the database that seem to satisfy the conditions that they want, some of those people maybe will say, no, I don't want to participate in your study, and it's their choice. If too many such people say they don't want to participate in the study, then the study can't happen. So your counting query, even with no question of privacy, your counting query can give you a kind of false positive. Similarly, it may be that everybody who has this illness or this condition is really willing to participate in the study. But you were conservative, and whereas you needed 200, you checked to see if there was 220 because you expected some people to say no. So if the database in fact only contained 205 and they were all willing, you'll still say, oh no, I'm not going to bother with this, because you'll make this error. So you can have errors even without privacy when you're trying to guess whether it's worth trying to recruit the patients. You can have both false positives and false negatives. And it's very interesting that if you look at some of the things that people in bioinformatics or the medical informatics say, they don't understand that they themselves can get false positives of this type. So now what we're going to do is we're going to use privacy for the counting queries. And we could see what happens with different kinds of privacy conditions. So one of them would be this sort of using this Gaussian thing where we just use delta F over epsilon. Or you could use epsilon delta, or you could do epsilon 0. And so you're going to have errors either way. And this is what the probability distribution looks like on your errors in the no privacy case, where you assume it's kind of Gaussian, or concentrated case, epsilon delta, and epsilon 0. So this is a sort of motivator for continuing to pursue these kinds of questions, because you get some error, but so do the non-private people, and you get less error than you do with these other notions. All right. So that's what I prepared. It's a short lecture, but questions? We covered a lot of material. Yes?
You said that logic noise is it will fail when we have insanely small probabilities. So I am unable to get that picture. How does it?
So as k increases, the probability of having a k epsilon privacy loss drops exponentially in minus k squared over 2. So if a bad thing is having a k of 5, the probability of that is at most e to the minus 12 and a half, or something like that. So that's the sense in which we're saying that bad things happen with very small probability. As it gets badder and badder, the probability of it happening is dropping really, really fast. It's worth thinking about. I mean, we haven't talked about what are the semantics, really, of an epsilon privacy loss. And one of the reasons we haven't talked about it is that we don't really understand it. But given that we don't understand it, it didn't seem like a really bad idea to push it farther in this particular way.
One thing about Gaussian noises, the point is that you like flat text, noise is disproportional to the delta, to the sensitivity. But x squared changes a lot if x is very big and you add that's the delta. So that's the trouble we shouldn't be in the Gaussian noise. The Gaussian case, you just have a certain amount of x, e to the minus x. So the change won't be the same factor, whatever x is. But Gaussian x is a lot, x squared changes a lot. Derivative x squared is x.
It's true. Yes?
I was trying to understand, you said that the privacy loss is a random variable.
I'm sorry?
You said that the privacy loss can be thought of as a random variable.
Yes.
So if you understand correctly, then the random variable is
Can you write it? Can you write on the board?
So is this what we understand as the privacy laws of a mechanism?
No, X1 X star not fixed. Right?
Max overall, we should say overall x comma x dash among the databases.
Right.
That's the infinity. But
I think that for now what we have to do is we have to fix x and x prime. Because we're into the epsilon delta world. So we have to fix x and x prime in advance, and now we want to ensure that the
randomness was only in the coin flips that M does, not the noise that M adds.
It is.
It has to be fixed. So is it a maximizing thing that we call as the privacy laws, or is it an expectation over all adjacent x's?
It's a maximum that we need to bound.
So that's why I thought this would be the already pinning down what is that random variable that we are talking about.
Okay, so I think that you're right, and I think that I'm slopping. So once you fix x and x prime, you can talk about the privacy loss over x and x prime as you fix x and x prime, now you run your experiment on the database X that defines a privacy loss with respect to x prime. And that's our random variable now.
So the question I wanted to ask was, so in the first epsilon 0 case, we were demanding that we
Yes.
use that most epsilon.
Right. So that's the difference between, that was one of the differences that I pointed out between epsilon 0 and epsilon delta, that you, like in that example I gave with me having different properties, if you chose the properties afterwards, you would definitely fail here. So you have to fix, okay.
So epsilon is PM at most epsilon delta private differential privacy, PM is at most epsilon with probability 1 minus delta epsilon.
In the epsilon delta case.
Generalization that we are pointing out towards the end.
Right.
Demanding that PM is bounded by some function instead of just an epsilon, just a two-parameter way of bounding it. Like we allow PM to be bounded by some function. Is that the kind of
Yes. Yes. And that function I want to be very, I didn't say this, I want that function to be tightly concentrated around its mean. Just as in the case that we were discussing here, this is very tightly concentrated. Well, it's around. Sorry. We have an expectation, and we know that we're not getting very big at all. So we're also not getting very far from our expectation. So I think that it will be to bound it by a function that is a tightly concentrated function, like this Gaussian. It would have mean epsilon squared rather than 0. Right? I think, as I said, it's under construction, but it seems plausible. Other questions? That was a good question. Other questions? Yes?
I'm trying to state inclusion of this data regions where the privacy loss not unbounded and principal going to be that. So is there, can we analyze where these regions might happen? It would be possible
Right.
to try and decoy record.
Yeah.
Where there's just junk data, so even if I lose the privacy of data, it doesn't matter.
Do you have in mind that you'll put in some decoy records and maybe you'll sample a record and release it, and that there will be some chance that it's a decoy and therefore it's not compromising anyone's privacy? Okay, so one possibility is you won't hit a decoy when you sample, you'll hit a non-decoy, a real person. And then in some adjacent database, that real person isn't there. So in that pair of adjacent databases, the probability that that real person is harmed in your method, in one of them, is something like 1 over the size of the expanded database, real database plus decoys. In the other one, it's 0. So with probability 1 over the, let's say, M, the bigger database, the expanded database, the privacy loss will be infinite. Now, so you have your real database, and you've added some decoys. So this total thing, let's say, has M rows in it. In the adjacent database, this part, okay. This guy is missing. Him is missing over here. This part is exactly the same. And maybe these guys, these decoys, may be the same. Now, over here, the chance that we violate this person's privacy, if you select a row at random, is going to be 1 over M. Here, the probability that you will hurt that person is 0. So this ratio is unbounded, and this event isn't so unlikely. They're not. I'm telling you it doesn't work to add decoys. That having decoys in the database doesn't necessarily protect the privacy of somebody who's in the database.
Basically, having decoys in some sense is like add noise, right? Not a structured noise.
Okay, so what I was analyzing here was the mechanism where you choose a random row and you publish it. All right. Now, you are sort of right that if the only thing that we're doing is counting queries, and we add decoys, sort of very random-looking decoys, then that's like adding noise. But it doesn't have a lot of noise in expectation, first of all. And if you ask several queries, you'll start to detect the difference between having somebody here and not having him here. That was kind of the heart of the proof that I mentioned yesterday, where the adversary had in mind 2 adjacent databases, and there was a gap of 1, and he asked a bunch of random queries, and that one guy kind of asserted himself periodically, right? So the same thing will happen here. So it'll protect you in some sense for a little while, but it won't protect you for very, very much.
No, I'm just trying to avoid the database. I'm kind of certain that the data regions are going to be randomly distributed. But
I don't know why you think they're randomly distributed. I don't know anything about them. All I know is that they aren't big. Whether they're randomly distributed or not, the delta region, the part of the probability space where things are very different.
it's random in the sense we don't know any information about where it's going.
But that doesn't. He took the words out of my mouth. That's not random. We're ignorant, but it's not random.
We have no information about where the regions are going. But if we can get some information about where the regions are going, we can plan because there.
It doesn't really work. Think about some specific mechanisms and some specific, and start attacking them with different sorts of queries, and you'll see that it doesn't, decoys, they work for a little bit, but they don't work a lot. Other questions?
What was the reason why the local sensitivity scaling the noise to local sensitivity?
Well, let's try to reconstruct that. The good thing, whenever you're trying to show something that something is not differentially private, is that differential privacy gives the adversary a very unreasonable amount of information. He lets the adversary, for example, choose a pair of databases that differ only in one row, and he knows everywhere where they agree, right? So somehow what you have to do in order to answer your question is you have to find a pair of adjacent databases where in one case the noise would be big and in the neighbor it would be small. And then he asks a query where he knows pretty much what the answer is going to be. And if the thing he gets back is like a standard deviation for the big noise, then he says, oh, it's really likely that I'm in that case. So,
You can ask the same query a few number of times and estimate the noise.
right, exactly. Or again, if he knows the answer, even just from one sample, he could say, oh, I would be very unlikely to have gotten that had we been in the neighboring insensitive case. This actually, though, I mean, you really have the feeling that most things that people ought to want to be learning from a statistical database should be pretty insensitive. And you really do want to be able to take advantage of that. It's like, what is a statistical analysis if my presence or absence in the database would completely change the answer? What does that mean about a statistic? It's about Cynthia, you know? It doesn't make any sense. And so it's possible that for many things that you want to do, they'll be stable in a lot of cases, and this kind of quick testing could work out well. Although then you have to worry about the computational complexity of the test. And as you might have noticed, I haven't been talking about computational issues. Yeah. More questions?